We looked at the classification of bones by composition, by shape. We looked at some bone histology. Now let's move on and talk about bone growth. So in order to grow, you need to have nutrients. How do bones get nutrients? That's right, blood vessels. All the cells of your body get their nutrients from your blood. That's one of the most important functions of blood, carry nutrients to your cells and to carry waste products away. So there are periosteal arteries that supply the periosteum. There are nutrient arteries that enter through nutrient foramina and supply compact bone of the diaphysis and red bone marrow. You've seen these nutrient foramina before, haven't you, when we did the lab? Remember the supraorbital foramen, the mental foramen, the infraorbital foramen? That's what those little holes in bones are for. It's for the nutrient arteries to get in. There's also metaphyseal and epiphyseal arteries supply the red bone marrow and the bone tissues. This is not a huge slight, just emphasizing the fact that you can't make bone without blood. So, bone formation. Bone formation, called osteogenesis, literally genesis, create, osteobone, osteogenesis, create bone. Ossification is another word meaning just to make bone. This happens when mesenchymal cells provide the template for subsequent ossification. So, two kinds of ossification occur, and I want you to know just the basics of what they are. Intramembranous ossification is the formation of bone directly from or within fibrous connective tissue membranes. Now, as it turns out, this is an unusual way to make bones in the sense that at least not most of the bones of your body are made this way. The flat bones of the skull, like the parietal and the occipital and frontal, they're made this way, and your clavicles. And it has to do, you see the embryo in the lower right, has to do basically just with the way you were when you were forming, your head tucked down like that. The cranial bones and the clavicles all came from the same place, basically. So those are the only bones formed by intramembranous ossification. Thin layers of compact bone with spongy bone in the middle. All the other bones of your body are endochondral ossification. And once again, root words here are so important. I just ate dinner and I'm still drinking things. So endochondral. Endo means inside. Chondro. Anytime you see the word chondro, that's cartilage. All right, get used to that. Chondro. C-H-O-N-D-R always means cartilage. So endochondral means basically that you're making bones from cartilage. Like I said before, it's like you take, clay and you make a model of the bone and then it hardens into bone. That's called endochondral ossification. Most of the bones of your body are made that way. Now, there are two growth centers, the primary and the secondary. You don't really have to know anything about those. I won't ask you about those. But I will expect you to know the next two terms, interstitial and appositional growth. And those are fancy names for interstitial means growing in length. Appositional means growing in diameter. Bones have to grow both ways. Think about it. When a baby is just born, think about the femur of that baby. Is the femur of the baby as long as your femur? I hope not. Bones have to grow lengthwise. That's interstitial growth. But also, when a baby gets older, is your femur still the same width as the femur of a baby? No, of course not. You've got a lot more weight to support. So appositional growth means the bones grow in diameter. Both types of growth have to occur in order for you to turn out okay. Let's look at interstitial growth first. Growth in length. So this is the epiphyseal plate. So look in the lower left, you can see the epiphysis, that's the femur right there. You can see the epiphysis of the femur. Then you can see the diaphysis, the shaft. In between was the metaphysis. And remember, I said I didn't really care so much about the metaphysis except for the fact that that's where the epiphysis is, the growth plate. And the word is chopped off in that diagram. But that line where you see there's a blue line marking the epiphyseal plate. That's how bones grow in length. So cartilage cells are produced by mitosis on the epiphyseal side of the plate, and then you lay down bone on the other side. So in other words, the cartilage keeps dividing and growing to make new cartilage, and it leaves behind bone, kind of like those paving machines. As they go down a street, they leave pavement behind where they went. So yeah, The epiphyseal plate, as it grows outward, so that femur, it would be growing, the head would be growing to the left. As it grows to the left, you would have more and more new cartilage cells, and to the right, below it, you would be laying down bone cells. Somewhere between the ages of 18 to 25, typically, the epiphyseal plates close. That's just the normal way it works. If otherwise, people would grow to be, you'd keep growing in length your whole life, you'd end up being, 200 feet high, and that won't work. It'd be very hard to get into your car if that were true. So the epiphyseal plates close, and that's when growth and length of the bone stops, and that's when you no longer grow any taller. So cartilage cells stop dividing, and bone replaces the cartilage, forming the epiphyseal line. And I want you to know that difference. So the epiphyseal plate means that there's still cartilage there and it's still growing. Epiphyseal line means that the cartilage is no longer there. It's now bone, and therefore you cannot grow any more in height. So that's why growth and length stops by around age 25. At age 25, you're usually as tall as you're ever going to get. Oftentimes for females, by the time you're around 16, that's about as tall as you're going to get. And for a lot of males, your height at around age 18 is often about as tall as you're going to get. But it can continue all the way up to like 25. So look in the upper right, see the epiphyseal plate? When you do an x-ray, you can see a little gap there. Why? Because the epiphyseal plate is made of cartilage. So the bone is much more opaque to the x-ray than the cartilage is. So the bone stops the x-ray, the cartilage lets it go right through. And then down in the lower left, see that? You've got a tibia and a fibula coming down and joining a talus. And see how there are spaces down there? Those are epiphyseal lines. Sometimes they find like a dead body out in the desert, and they bring it in and examine it. And let's say it's a dead body that's 5'1". Well, is that a short adult, or is that a child, a high schooler or whatever? Well, one of the ways they can tell is to x-ray it. If you see epiphyseal plates, then it's somebody who's probably under the age of 25. If you see epiphyseal lines, that means it's an adult. So, see, once again, imaging coming through. So that was epiphyseal or interstitial growth. Let's look at appositional growth. Growth in thickness, growth in diameter. So in the lower left, you see a nice little graphic, an animated GIF, showing appositional bone growth. So we see the inner shaft of the bone, we see the periosteum and the endosteum. So when bones grow in diameter, both of those have to grow. That's why there are osteogenic cells in both the endosteum and in the periosteum. And remember, which layer of the periosteum are they in? Are they in the fibrous or the osteogenic layer? Yeah, the fibrous layer is where muscles attach. It's the osteogenic layer where you have bone growth. So I think that bottom left illustration is that shows very well how bones grow in diameter, how bones grow in width. Both the inside shaft and the outside circumference both have to enlarge. So you see that diagram there on the right, those 4 phases. I'm not going to ask you specifically to give those back to me on exams, but I do want you to be able to just take a look. Look at number 1. So here you've got the periosteal ridges. Here you see a periosteal blood vessel. So this is a blood vessel that's on the outer surface of the bone. Look what happens by the time we get to number 2. The lamellae, all right, those circles of bone, are starting to enclose around it. And then by the time we get to 3, they're really starting to enclose. And look what happened by the time we got to 4. What started as a periosteal blood vessel is now the blood vessel in the middle of a central canal. So that's what happens as bones grow in width. External blood vessels end up becoming central canals as the bone grows in width, and you create more and more osteons, okay? I won't ask you to tell me specifically those 4 steps on an exam, but if I asked you to, I would want you to explain to me basically how a bone can grow in width, and that's what's shown in that diagram. So how about this? Where would you find trabeculae? In the epiphysis of the femur, in the outer layer of the parietal bone, in the diaphysis of the ulna, in the compact bone layer of metacarpal 4, or in the compact bone layer of the femur. So, pause the video. This shouldn't be too hard. Where do you find trabeculae? What kind of bone tissue do you find them in? Yeah, that's right. You would find them in the epiphysis of the femur because that's where you have spongy bone. All those others would be compact bone. The outer layer parietal bone, compact. Diaphysis of the ulna, compact. And of course, the compact bone layers are compact bone. Well, trabecular are only in spongy bone. So, what affects bone growth? Lots of things do. Nutrition is a big deal. You have to have enough calcium and phosphate. And that's why, again, a lot of growth deficiencies, people in parts of the world where they don't get enough food, oh my gosh, they don't stand a chance. They can't possibly develop normally because without the proper nutrients, you can't grow. So obviously, since bone was that matrix of collagen fiber and the hydroxyapatite, you need amino acids to make proteins like collagen, and you need calcium and phosphate in order to fill in the matrix. Calcium and phosphorus for bone growth. Vitamin C to make collagen. That's important in the formation of collagen proteins. Vitamin K and B12 for protein synthesis. We talk about this a lot in Bio 202. Vitamin B12 is necessary for cells to divide. And in fact, like with your blood, if you don't have enough vitamin B12, you can't make enough red blood cells, something called pernicious anemia. So watch for that in Bio 202. You have to have sufficient level of specific proteins. So during childhood, insulin-like growth factor. Remember, we've mentioned growth factors before. So nerve growth factor, epidermal growth factor, insulin-like growth factor. These are hormone-like substances. They're very important in regulating growth throughout the body. Lots of research these days on growth factors. Promotes cell division at the epiphyseal plate. So notice, hormonal and growth factor deficiencies could also cause abnormal growth. If someone has grown abnormally, you can't just look at them and know for sure what happened. There are lots of possibilities, all right? Could be mineral insufficiency, could be protein insufficiency, all right? That's why it takes some investigation to find out what's going on. Human growth hormone, thyroid hormone, and insulin are also extremely important in allowing bones to grow. That's why, once again, any kinds of problems with any of those things can lead to a growth deficiency. At puberty, you go through the growth spurt, those sex steroids come into play. So estrogen and testosterone stimulate the sudden growth and modifications of the skeleton to create the male and female forms. Those are both steroid hormones, and notice how similar they are. As we'll talk about this in Bio 202, all of your steroid hormones are made ultimately from cholesterol, and they all look almost identical. Estrogen, aldosterone, cortisol, testosterone, vitamin D. These are all, cholesterol has this very unique 4-ring structure. And so that's what you see in all of the steroid hormones, this very distinctive 4-ring structure. And notice how testosterone and estrogen are very similar. In fact, your body can convert back and forth between them. So they both are very important. And both males and females have both estrogen and testosterone. It's just that estrogen, females have relatively more of that. Males have relatively more testosterone. So a few hormonal abnormalities in bone growth. Oversecretion of human growth hormone during childhood produces gigantism, sometimes just called giantism. People who have giantism normally have proportional features, but they're taller. So that guy there is George Mirasan. He played for the Bullets in the NBA, and I forget how tall he was, 7'7", something like that. But look and see how he looks like a normal person in terms of his proportions. He's just really, really tall, okay? So normally gigantism, you look very typical. You're just very, very tall. In contrast, if you start over-secreting human growth hormone during adulthood, that results in something called acromegaly. Greek root words acros, high, and megalos, large. You'll be high and large. So remember, the epiphyseal plates close by around age 25. So what happens if you're secreting too much growth hormone after your epiphyseal plates close? Can you still grow? Can bones still grow in length? No, they can't. Once the epiphyseal plates turn to epiphyseal lines, no more interstitial growth is possible. But can bones still grow in other ways? What's the other kind of bone growth? Yes, appositional growth. So bones can grow wider. So as a result, people with acromegaly usually have very large facial features as the bones of their skull grow wider and like their teeth start getting more widely spaced. large hands as the bones of their wrist and stuff grow, and that makes their hands larger, their feet larger. So people with acromegaly look unusual. They look very thick and very wide. They have an unusual look to them. It's usually, you can really spot it. Caused by a benign tumor of the pituitary gland. That's a very common cause. Today you can treat it with drugs and surgery, but back in the old days, it wasn't always possible. So one person with acromegaly was Andre the Giant. You can see him there in the lower right. Now apparently he had gigantism when he was young, but then he continued to oversecrete human growth hormone, so it turned into acromegaly. So he was both very, very tall, but also very wide. Look at the size of his hand. It's as big as Fezzik's head. If you've never seen The Princess Bride, you're deficient in life. You need to watch that movie. It's hilarious. It's wonderful. Classic movie. Should be on everybody's list. But yeah, he has enormous hands. That's very typical of acromegaly. Undersecretion of human growth hormone or thyroid can produce short stature. Sometimes what's called dwarfism. Terms come in and out in medical practice. I'm not sure the current status of the word dwarfism. Short stature, I think, is a pretty safe way to go. Both men or women that lack estrogen receptors on cells grow taller than normal. That's not really critical, just pointing that out. Estrogen is responsible for closure of the growth plate. So once again, when you look at someone who has abnormal height or whatever, you can't tell just by looking what's going on. It takes a lot more investigation. And here's another person with acromegaly, kind of a famous person. His name was Maurice Tillet, lived from 1903 to 1954. He had acromegaly. He was born in Russia, and he was a professional wrestler known as the French Angel, one of those WWE guys. So look at him. Does he remind you of anybody? This is still kind of a rumor, but I think it's been pretty much followed up on, and I think it's pretty clear at this point that he in fact was the model for Shrek. He was around, he was wrestling back when Walt Disney, when Disney was creating all this stuff, and so, I don't know. I guess Walt Disney was dead by the time they made Shrek. I don't know. Investigate it on your own. Don't believe anything I tell you. Look and see what you can find out about Maurice Tillet and Shrek. And then you can talk to each other about it.